Hello everyone, I'm Lucas Villagra from Universidad Nacional de Córdoba, Argentina, and I'm going to talk about using Q-curves and Hecke characters to solve Fermat-type equations. But first of all, I want to thank the organizers of this session to give me the opportunity to present this poster. This poster is based on two papers in collaboration with my advisor, Ariel Pacetti. And in the first part, I'm going to present the modular method, which is used to solve different equations, such as Fermat-type equations. And in the second part, I will try to show the approach of using Q-curves and Hecke characters in this method. And I believe that the most easy way to introduce this method is starting the first time that it was used. So let's start with the sketch of the proof of the Fermat-type theorem. Remember that it says that if n is a natural number bigger than 2, then the equation x to n plus y to n equals c to n has no integral solutions except from the trivial ones, thus that has a coordinate equal to 0. And it is easy to see that we can assume n equal to p, a prime number. So the proof consists basically in a few steps. We can assume that we have a solution ABC, and to this solution we will attach an elliptic curve E, which of course depends on the solution, and it is usually called a phase curve. And this is the discriminant of the curve. It is basically a constant, 2 to minus a, times something that does depend on the solution, but it is raised to p. Then we will use that the curve is modular. This is in fact was the last piece of the proof. It was proved by Wiles and Taylor-Wiles, but now we put it here. And since the curve is modular, we know that there exists a new form G of weight 2 trivial negativus and level exactly the conductor of the curve, such that the representation associated to this new form is isomorphic to the representation of the elliptic curve. This representation that we obtain when we look the action of the absolute value group on the p-torsion points of the curve. So now we are in condition to apply the lowering the level Rivet theorem, which basically says that if the representation is absolutely irreducible and L is a prime other than P, such that P has multiplicative reduction on L and P divides the L valuation of the discriminant, then we can remove L from the level of the new form. And moreover, in this case, since the representation is finite on P, I don't want to say what this means, we can also remove P. So as a conclusion, we have that there exists a new form F of weight 2 and level 2, such that its representation is isomorphic to the representation of the elliptic curve. And finally, we have a contradiction. Remember that we started supposing that we had a solution, so we need a contradiction. And in this case, it follows directly from the fact that there are no new forms of weight 2 and level 2. So what is the modular method? It basically consists in these 4 steps. So let me give a brief summary. First, we need to construct a curve from a putative solution such that the discriminant of the curve is of this form, a constant, which does not depend on the solution, times something that does depend on the solution, but it is a p power. And also, since we later want to use the Rivet result, we want the primes that divides D to be of multiplicative reduction. Later, we will use that the curve is modular. This is directly, it follows directly if the curve is rational. And also we know that this is true if the curve is defined over a real quadratic or cubic extension, for instance. And then we have to lower the level to look for a new form of a specific type which does not depend on the solution. And finally, we need a contradiction. Remember that it was trivial if, in the case of the Fermat-type theorem, but in general, we need to use different arguments to eliminate all the possible new forms from the above state. So I think that one of the main reasons why we expect that this method works for other equations is this theorem of Darmon and Granville, which says that if a, b, c are fixed integers and pqr are primes such that 1 over q plus 1 over q plus 1 over r is less than 1, then this equation of here has a finite number of primitive solutions. We say that a solution x, y, c is primitive if x, y, and z are pairwise coprime. So let me show how this works with a specific equation. Let's focus in this equation of here. X to 4 plus d times y squared equals c to p, where d is a positive integer. The case d equals 1 was studied by Ellenberg, and the cases d equals 2 or 3 were studied by Ulefe and Jimenez Burgos. And one of the things that we did with Ariel was study this equation of here for an arbitrary number d. So let me show this. If we put d equals 6, let's see that this equation does not have non-trivial primitive solution if p is bigger than 18. So let's follow the steps of the modular method. Suppose that we have a solution ABC, and let's consider this curve, and notice that it is not a rational curve. It is defined over an imaginary quadratic field. This is the discriminant of the curve, and it is not trivial that it is modular. We have to use the fact that it is a Q-curve. This means that it is isogenic to its Galois conjugate, sorry. And to define this isogeny, we need to add a square of -2 to the field of definition of the curve. And now we know that from a reverse result, we know that for all Q curves, there exists a twist such that the associated representation descends to Q. So what we did was define explicitly the Hecke character for which we have to twist to descend the representation. So to do this, or to show this, let me define epsilon and c minus 2, the characters corresponding to the extensions q square of -3 and q square of -2 via classical theory. So we have this theorem which states that there exists a Hecke character here such that satisfies these 3 conditions. The third one basically says that this is the character for which we have to twist. Notice that we are twisting for this character. The second one gives information about the level of the new form. Notice that the only primes that appears in the level are this one that divides divides d. In this case, d. Remember that it was 6, and these primes later will be removed with the level, lowering the level result. And the first condition says that epsilon will be the Neventipus of the new form. So in order to apply the lowering the level result, we need to use this Ellenberg theorem, which says that if K is an imaginary quadratic field and E is a Q-curve without Cn, there exists a bound n such that for p bigger than n, the representation is surjective. And remember that we are looking this equation here. So if we have a solution ABC, a primitive solution, then C must be coprime with 6. So there exists a prime Q bigger than 3, which divides C. Then E must be a multiplicative reduction on Q, so it does not have Cm, so we can use Ellenberg's result. So we have a representation with big image, so we can lower the level. So there exists a new form f of y2 on level n equals 2 to e times 3, where e was 8 or 9, such that the representation of the new form is isomorphic to the twist of the representation of the curve. And now we need to discard these all possible new forms, and we will use Mason's trick, which gives a way of compute this number b, which depends on a fixed number q. So later we can vary this value of q, such that p divides b. And notice that we have to compute the trace of the elliptic curve, and the elliptic curve depends on the solution. So what we do is vary the possibilities of a and b modulo q, and we compute this product. So we have that p must divide this product, and we say that we have a bound if we are lucky enough, because if this product does not vanish, we have a bound. Suppose that this product equals to 10, then we have that p must be 2 or 5, but we can say anything is if this product equals 0. Okay, so we compute the first space, and it has 10 new forms. Computing this number c for q equal 5, equal to 5, we have that we can discard all the new forms for p bigger than 7, and the same happens to the second space for p bigger than 19. So as conclusion, we have that if p is bigger than 19, then there are no non-trivial primitive solution of this equation. So as I was said before, we get a receipt of what do you have to do for an arbitrary number d, and we also gave explicit bounds for d equals 5 or 7. And as the same way, we can consider this equation. In the case d equals 1 was solved by Bennett and Chen. The case d equals 3 was solved by Topsenes. And we also gave a receipt for an arbitrary number d, and we treated the cases d equals 2, 5, 6, and 7. So I think that natural question is what happens when d is a negative number. While we have two issues. First, remember that the curve was defined over q of square of minus d. So in this case, it will be defined over a real quadratic field. So we will have more units. And remember that in order to see the well definition of a Hecke character, we need that the Hecke character be trivial on units. So in this case, we will be more difficult to see the well definition of the Hecke character. And another problem is that we could have solutions ABC with C equal to 1 or minus 1. So this solution could be a solution for all the possible values of P. So this was treated in the second paper, and we have results of this kind. If P is bigger than 19, such that P is different from 97, and P is congruent to 1 or 3 modulo 8, these conditions is because we have to discard the new forms with Cn. Then this is the only non-trivial primitive solution of this equation. Notice that it is a solution for all the possible values of P. So I think that was all I wanted to say. These are the references, and thanks for your attention.